Namaste, welcome to the class. Hope you are doing well. We have discussed about how to dope a pure semiconductor with trivalent impurities, pentavalent impurities, and the doping of pentavalent impurities results in many free electrons, and that gives an n-type semiconductor. Similarly, doping a pure semiconductor with the trivalent impurities creates more and more holes and more vacant bonds, and that gives more majority carriers, holes as majority carriers, and that is why it is called p-type semiconductor. Now if you develop such a p-type and n-type semiconductor in a single wafer, single silicon crystal, what happens? Single semiconductor crystal. That's what we were discussing about in the last class. So if you have a single semiconductor, then one half is doped with the pentavalent impurities, so it contains plenty of electrons as majority carriers, and there may be few holes because there may be few thermally excited electrons that creates holes. Here in all these electrons, if you ask, all these electrons are not because of the phosphorus. There may be some few electrons because of thermal excitation, and so that creates equal number of holes. So majority carriers are electrons, minority carriers are holes, and here you will have many holes because it is doped with the trivalent impurities. There may be few electrons here and there. So this is a p-type semiconductor, this is n-type semiconductor. It formed on the same single crystal. Now when they are formed on the same crystal at the junction, what you call p-n junction, this is p-n junction. The whole device itself sometimes called p-n junction, right? P-n junction diode. So there is a migration because there is a higher concentration of electrons on the right side, that is n side, and there is a higher concentration of holes in the left side. There is a lower concentration of holes here, lower concentration of electrons here. So there is a diffusion of electrons from n side to the p side, diffusion of holes from p side to the n side. So when an electron comes from here and reaches the hole, this part, only this part, totally p-n junction is neutral. This part of the that device will lose one electron. So actually the pentavalent atom loses one electron, and that electron comes here. Now if you ask that pentavalent atom, where is that free electron which was not forming the bond, it is answerless because it has gone to the other side. So this gets negatively charged, positively charged, because it has lost one electron. That electron comes here, and that is here, and now it is an immobile charge carrier because it has completed one bond, and that bond is completed and that is immobile now. That is why this is called depletion layer, and automatically here is an ion which is immobile. That phosphorus atom has become an immobile ion, and this happens at the junction very fast. At the junction it happens very fast and that's why this region is called depletion region. Depletion layer. The layer which contains immobile ions, and because of the migration of electrons and holes across the junction. So this develops a negative charge on the p side and a positive charge on the n side. Remember, on the n side electrons leave and come to this side, that is the diffusion. On the p side, holes cross the junction and move to the n side. So there is a diffusion of electrons and holes across the junction. Diffusion of majority carriers, I can say easily. Majority carriers cross the junction, but as they cross the junction, the two ends will get charged, and there is a positive charge here since it has lost an electron, and this has gained one electron, it is negatively charged. So this negative and positive charge will grow, and that produces a potential difference, because as more and more electrons come to this side, the further electrons will find it difficult to come to this side because these electrons are opposed by these electrons. So at one point what happens is, all the electrons which have come here and combined with the bond, or they have engaged in the bond and making the boron atoms or trivalent atoms negative here because it has got one extra electron. these negative charges are successful in avoiding all the electrons coming out from here to here. So electrons which have already arrived here will be successful in avoiding the further motion of electrons. Similarly, this positive charge will avoid the further motion of holes. So electrons and holes cannot cross the junction after some time, because already arrived electrons and holes will oppose it by developing their own potential called barrier potential. So here you will get, this acts like a battery now, with a positive charge here, negative charge here, and that battery will have a potential difference, a voltage, which doesn't support the motion of electrons and holes. This doesn't support, it avoids, because these electrons do not allow these further electrons to come. These positive ions don't allow the further motion of holes to the other side. So motion stops. Otherwise what would have happened is, all the electrons might have gone here and recombined with the holes, and this should have got positively charged and this side negatively charged completely. And that cannot happen, because the migration itself will start opposing. So for example, if you keep on putting bricks one by one, above the other, it is easier to keep the initial bricks, but when the height of the brick row becomes more and more, at one position you find it difficult to keep the bricks, because the height will go on increasing. So there is a saturation point, and the current due to this majority carriers flow. Majority carriers means electrons in N region, holes in P region. That current is called diffusion current. So diffusion current stops at a moment. Now, once the diffusion current stops, what are the things developed at the junction? We have a depletion layer which contains positive ions on the N side, negative ions on the P side. The trivalent atoms which have got one electron, and the pentavalent atoms which have lost one electron to the other side. And there is a depletion layer. So that barrier potential, where did I write? I didn't write it. Barrier potential avoids the further migration of electrons and holes. The extra electrons and holes, their migration is stopped by that barrier potential. So here is a plus and here is a minus. This acts like a battery. You know the symbol of a battery, right? So this itself, junction itself, acts like a battery. Okay, so this acts like a positive, this acts like a negative. This is like a battery, and this is barrier potential. Barrier potential avoids the further migration of electrons and holes. Okay, so further electrons and migration of holes has stopped, but you will get one more current now. That is called drift current. I'll write the word here itself. See, drift is, see, whatever has happened here, as soon as the junction is formed, whatever has happened here is because of the diffusion. What do you mean by diffusion? Motion from higher concentration to lower concentration. That has happened. So higher concentration of holes, movement here. Higher concentration of electrons, movement here. That has happened by itself. No external battery energy is required to move these charges from one point to another. So suppose you have one beaker filled more with water, another beaker less amount of water. If you connect them by a pipe, flow of water starts by itself, right? Higher concentration to lower concentration. Actually, this is not concentration. So higher pressure to lower pressure. If you connect it by a pipe, automatically water comes down here, water grows here. So there is a water flow. That doesn't need external energy to push. The pressure difference itself will make it to flow. But if you have free electrons in a material, for example, in a conductor, suppose you take a copper. This is not a semiconductor. If it is a copper, there are plenty of free electrons inside copper. Copper is a very good conductor. It's a metal. It has plenty of free electrons. Now, if these electrons have to flow in a particular direction, you must supply an external energy. You must give an external bias. We call it as bias. Bias means force them to do. Yes, you have to connect a battery. Now electrons are pushed to this side, and positive will attract the electrons. Electrons will move in a particular direction, and that gives a current. And this current is not diffusion current. This is called drift current. What do you mean by drift? Flowing for a particular reason, right? Whenever the bell rings, students will come out of the classroom, because corridor is having a scarcity of students and classroom is filled with the students. So you want to get a fresh air, you want to look somewhere outside and you want to relax your eyes, you come out. Because there is a motion from higher concentration inside the class to the lower concentration outside the class, corridor. That is natural flow. That doesn't require any pressure, external pressure. Suppose that doesn't require any external triggering or external battery. Suppose in the corridor students are wandering here and there. Suppose a teacher comes, all the students will start running towards one side. That is drift. It is forceful motion, right? All the students are forced to move on one side. That is called drift. Similarly, in a metal, whenever there are more and more electrons, free electrons, if they are moving randomly, and if you want them to flow in a particular direction, you have to connect a battery. And when a battery is connected, electrons drift. We use the same word. Drift means moving in a particular direction, and by colliding with some other electrons, and somehow they have managed to move in a particular direction. Now drift current starts coming over here. We have finished with the diffusion current. Sir, how come the drift current? Where is the battery? This itself acts like a battery. The potential developed across the junction, which avoids the further migration of electrons and holes, that itself acts like a battery. Now you see, these positive charges cannot cross the junction now, because these positive ions will oppose it. These electrons cannot cross the junction because these negative ions will not allow them, they will oppose it. Now what happens is, now you see this positive potential and see the minority carriers here. You forget about these positive, they can't cross the junction because already arrived positive holes, they avoid the further migration of these holes. These electrons can't cross the junction because already arrived electrons will oppose. Now if you ask these electrons, you ask them, this one, minority carriers, you ask them, they are very happy because you see, this negative will attract these minority holes. This positive on the other side will attract the minority electrons. So electrons can move because the other side positive may attract them, and these positive charges may move here. So because of the barrier potential developed, the minority carriers can cross the junction because of that barrier potential. So they create one more current, and this current is opposite to the current developed earlier, diffusion current. How does the diffusion current occur? Diffusion current occurs because of the movement of holes from P region to N region, electrons from N region to P region. That is in this direction, right? That is the direction of diffusion current. Now how is the drift current? Drift current is because of the minority carriers. Positive charges will move to this side because this is negatively charged. You see, negatively charged part of the diode attracts these positive charges. Positive side will positively charged side will attract these negative charges. So there is a drift, and that current is like this. Am I right? Drift current is in this direction because holes will move like this, electrons will move like this. Current is always opposed to the direction of motion of electrons. These minority electrons will move like this. Holes will move like this, minority here, minority holes, so like this. So they produce a current. That current is in the direction of positive charges like this, or opposite to the direction of negative charges, again like this. So this is drift current, and this is diffusion current. Are they opposite? So because of the barrier potential, at one moment drift current starts flowing across the junction, and when drift current and diffusion current balance, the flow stops. That flow will also stop. So at one stage, drift current and diffusion current will be equal. They will be equal, and now the diode is ready. The junction is ready, and PN junction is ready now. Sir, why it is ready? All the things are over. You have got positively charged one side and negatively charged another side, and some of the minority carriers have moved on the other side. They have produced drift current, which is equal and opposite to the diffusion current earlier produced, and two currents cancel each other now. The net current is zero. What is the use of this? Now the use comes. Now, sir, I want few more holes to move from here to here, few more electrons to run over from here to here. But they can't, because this barrier potential or the depletion layer doesn't allow them. So barrier potential, the potential junction potential, we have different names, that avoids the further migration of electrons and holes. It allows the migration of electrons and holes initially. Because of that, barrier potential itself is developed. But once the barrier potential is developed, the further migration is stopped of the majority carriers. Now I want more holes to go from here to here and electrons come over from here to here. So I want further migration. If you need further migration, you have to give a energy or potential and a potential difference which is more than this barrier potential. You have to give external energy, otherwise these electrons and holes can't move. Suppose you want to keep a brick which is more at a height more than what you can do. So you want to keep it. You have to get the help from somebody else. Somebody else should come and lift you and you can keep the brick. So you need an external biasing, external energy. So a diode is ready with the two, and a diode contains two regions, P-type and N-type semiconductors, and a junction, single junction. When two rods meet, you have a single junction. So diode is a semiconductor device containing two regions, P region and N region, and a single junction. Now that junction is ready. Now if you want to work with diode, you have to connect an external battery, and that type of energizing the PN junction, giving energy to the electrons and holes in the PN junction is called biasing the PN junction, connecting the external battery. And there are two types of bias, forward bias and reverse bias. So what do you mean by forward bias? What do you mean by reverse bias? We will see it now. That is the main thing. So a diode can be used in two ways, forward bias and reverse bias. As if, see, there are two ends, right, for this one, P side and N side. Of course, when you purchase a diode, I will show the diode later. I will bring it. It's very, very small one. If you cut the refill of your pen, and the nib and the refill of your pen, if you cut that small part, how much larger it is? That is the size of the diode. Very smaller one. Sir, can we see all these P and N regions? No, never. It is very, very small. And remember, the junction depletion layer width, you know what is the width of the depletion layer? It is 10 to the power minus 6 meters, in the order of micrometers. Micrometer range. It's such a small one. This may be few millimeters or micrometers, and this is also. So it's a totally smaller size, millimeter size, and you can't see that at all. It's a very smaller one. And also this is not seen because it is packed and it is given to you. Because if it is kept open like this, after this is developed in a laboratory, if it is kept open, dust, moisture, everything will spoil it, and external heat energy and all, that will spoil it. That's why it is packed in a small cage and it is given to you. So diode is ready. It has two ends, and the two ends of the battery, as if you connect two plugs, the two ends of the plugs to a plug key. You have two ends. These two ends can be connected to the battery, right? Which will you connect to the battery? So battery will always have a plus and minus. Will you connect P side to the positive, N side to the negative, or reverse it? P side to the negative, N side to the positive. Depending on that, we have two types of bias. One is forward bias and another is reverse bias. Okay, we will see that, forward bias and reverse bias. So biasing a diode means supplying energy to the junction, supplying energy to the charge carriers, electrons and holes. And diode can be biased in two ways, forward bias and reverse bias. Now a diode will always have a symbol, and it is like this. We will see why it is so. This is the diode, this is the P region, this is the N region, and these are the two wires given for the connection. Because the whole PN junction, that silicon base, will be kept inside a cage, and it is packed and it is given to you in order to avoid moisture and temperature and other dust particles sitting on it. So in order to avoid, it is put in a cage, so small package. So the symbol of it will have two terminals, P side and N side. Two external connecting wires will be given to you, because if you want to connect them to any battery, you have to have two connections, because you can't open it and connect it. This is the symbol, circuit symbol, because every time you can't draw the actual diagram of a diode in a circuit, you have to have a only symbol. Now, as if you have a symbol like this, right? What is this symbol? This is the symbol of a switch. Every time you can't draw a switch like this and something like this, it is very difficult. This is a switch. Similarly, this is diode. Now, what do you mean by forward bias and what do you mean by reverse bias? I'll take a diode, PN junction, this is P side, this is N side, and you know that here electrons are the majority carriers, very few holes, still few holes may be left with, and here holes are the majority carriers. Few electrons, very few electrons. Electrons might have come here and added with, completed some broken covalent bonds by filling them with the electron. So this has got negatively charged. This is the junction, and from the other side this has lost one electron. So this is having positive phosphorus ions or antimony or bismuth, whatever it is. Okay, now what do you mean by forward bias? Connecting the P side to the positive of the battery and N side to the negative of the battery is called forward bias. You can, because you said this has two terminals, where these wires will be connected outside and you can see them, you can connect them anywhere. So you have two terminals, and battery also has two terminals. So when you meet your friend, you have two hands, your friend is also having two hands, you can hold his hands and you can enjoy. Whether you hold his right hand to your right or left hand to the left, that is left to you. You can hold it like this also, anyway. So if the P side of the diode is connected to the positive of the battery and the N side of the diode is connected to the negative of the battery, then it is called forward bias. So forward bias is a type of supplying energy to the junction or electrons and holes, majority carriers or any charge carrier, by connecting positive of the P side of the diode to the positive of the battery, N side of the diode to the negative of the battery, because diode has two regions, P region and N region. This is a type of connection called forward bias. Okay, forward bias is over. Now what happens here? Now select a battery such that you can change the potential difference across this battery. Okay, you can change it. This is how we show it. If you show a battery like this, you see, if you purchase a battery from your shop, for example a dry cell battery, Nippo battery, Eveready battery, it will be 1.5 volt fixed, 5 volt fixed, 9 volt fixed. It doesn't change its potential difference. Whereas if you purchase a battery, electronic battery, there are some batteries where you can change the potential difference. You can vary the potential difference, and when you can vary it, we show it like this. Now we will take such a battery which can vary, say this is from 0 to 15 volt. You can keep on changing the voltage, potential difference applied. And remember, how will be the charges developed, how this will, depletion region will act like a battery, that is barrier potential. How it is developed? Electrons come here, this is negatively charged, and these electrons have left this place, so this is positively charged. So this is like a battery with the negative here and positive here. This barrier potential is avoiding, right? That potential difference across the junction, that is junction potential, is avoiding the migration of electrons and holes. That is why these electrons can't cross the junction because of this negative potential. Holes can't cross the junction. I am talking about majority carriers, and that is because of this. But minority carriers can cross, because this positive, negative charge of this can attract the minority, and positive charge of this will be attracted by the the minority negative charges may be attracted by this positive charge, so they can move. That has already produced a current called drift current. That is over. Now still some minority carriers will be remaining, because drift current also can't raise to a high value. When the diffusion current and drift current are equal and opposite, the migration stops. Now come to the point where biasing is applied. Now you see the biasing potential difference. Here we have connected positive, but barrier potential here, this side is negative. So there is a fight. This battery tries to push the majority carriers here. Who are the majority carriers? Holes. Holes go to the other side. I am giving the energy. Here negative, you see, negative, electrons. Majority carriers electrons. Electrons move to the other side. I give the energy. But barrier potential says, no, you are not allowed to go, because this negative opposes. So there is a fight. Who is stronger? He will win. Definitely in the beginning barrier potential will be stronger, because this battery is having different potential difference, and I am increasing it from 0, correct? Now as I increase it, the electrons and holes, majority carriers, electrons in the N side, holes in the P side, they start getting energy from the external biased battery. Battery will keep on giving energy to them. when the energy of these electrons and holes is greater than the energy given by the barrier potential. With how much energy that barrier potential avoids the migration of electrons and holes. When the potential difference of the battery is greater than the barrier potential, what happens is the migration starts. Electrons and holes will start crossing the junction. They will start crossing the junction and current will be produced. So when the forward bias voltage exceeds a certain value, when the forward bias voltage exceeds certain value, the current starts flowing across the junction and you get a current. But till this one is below the barrier potential, you don't get current. So if you draw a graph of current versus potential, forward current. So I will disconnect this and I will connect an ammeter. Actually it should be microammeter. If I connect a microammeter and if I draw the current versus voltage, if I draw the voltage here, potential difference and current, I will write. I should be actually in milliamperes. Okay, forward current is very low and it is in milliampere. So if I draw a graph of milliampere current versus voltage along x-axis, then I will surprisingly find that initially when I give more and more forward bias, the current is lesser and lesser. No current axis. I am increasing the voltage, no increase in this direction. But once this the forward biasing voltage crosses this barrier potential, current starts rising up. Can you understand this? Now the current starts rising. For this rise, you need not have much biasing voltage. Once you cross this one, it becomes easier, right? Once you are lifted above the height of the bricks, you can keep the bricks easily. So somebody must give the energy which is enough to keep the bricks at the top. But when you are on the ground, you can't keep it because already have kept so many bricks and further keeping of bricks is not possible. So when somebody come and lift you, you get enough energy and you start keeping the bricks. Till that you can't do. So when this forward bias voltage exceeds some voltage here, and that voltage after which the current rises sharply, say straight line, this is called cut-in voltage or knee voltage. The forward bias voltage, the energy given during the forward bias, you know what is forward bias, connecting the positive of the battery to the P side, negative of the battery to the N side. And that forward bias voltage after which current rises sharply, because these electrons and holes are waiting for somebody to help them. And when the sufficient help is given, they can cross because they need not care about this barrier potential. The potential which avoids the migration of holes and electrons, that won't be carried by all these electrons and holes because they are getting support from somebody else, so they can cross the junction. Once they can cross the junction, current starts flowing in the diode and you get an enormous high current. Now the diode offers very less resistance because you get a high current in the circuit. So diode conducts during forward bias. Conducts. But only after cut-in voltage. So how do you define cut-in voltage? The cut-in voltage is the minimum voltage above which diode starts conducting. Cut-in voltage is the voltage after which current rises sharply. You can have any definition. Once the current starts flowing in the circuit, the meaning is electrons and holes are crossing the junction. So you get an enormous amount of current. So diode conducts during forward bias. Its resistance is very less resistance, very low resistance. You know what is resistance? Opposition to the flow of current. That is measured in ohms. Opposition to the flow of current is called resistance, that is measured in ohm. So resistance decreases, current starts flowing in the circuit and diode conducts during forward bias. That's why in the symbol you have an arrow mark here like this. So it conducts. Now go for the reverse bias. The graph you can see. Sir, what is the resistance? You say that it is very low. You get the slope here. You can get it V by I, because R is equal to V by I, voltage by current. Voltage is this one, slope, right? This is, sorry, voltage is here and current is here. So you get delta V by delta I, you will get resistance. it is very less. You see, delta V is very less, delta I is very high because the curve is very steep here. So you have to get the straight line part where you can find out the resistance. Okay, it is over. Forward bias is over. Now see here, we have given forward bias. P side of the diode is connected to the positive, N side of the diode is connected to the negative, and current flows from holes to the holes move from P to N region, electrons move from N to P region. So there is a current like this in this direction. Shall I write it like this current? Right, in the direction of holes, opposite to the direction of electrons. So we write voltage and current in the first quadrant, both positive. But when we go for the reverse bias, what do you mean by reverse bias? The P region of the diode is connected to the negative of the battery, and N region of the diode is connected to the positive of the battery, like this. This is called reverse bias. Again, the same battery where it can be varied. So what do you mean by reverse biasing diode? When the P side of the diode is connected to the negative of the battery, see, this is not positive and negative. This is not positive and negative. This is P region where there are more holes, more positive charge carriers. N region, the region where there are more electrons, negative charge carriers. So when P region of the diode is connected to the negative of the battery and N region of the diode is connected to the positive of the battery, the process is called reverse bias. Okay, reverse bias. So if you connect the diode like this now, what happens? Now you see the barrier potential and what the potential difference you have applied, external energy you have supplied. They are identical. Already this barrier potential developed across the junction is not allowing the charges and majority carrier charges to flow. It is not avoiding, it is not allowing them. It is avoiding the further migration of electrons and holes. And accordingly this barrier potential is developed. Now you see this one, very similar to this one. In addition to barrier potential, we have another external bias, another external power supply which doesn't allow the charges to flow through. Now what happens here is the electrons and holes are made to move away from the junction. And if they are made to move away from the junction, how can it be the current flow? It should flow from one N-type material to a P-type material or P to N. Somehow it has to move. But here it is not allowed. The these ions will be attracted away because this battery can attract these ions. So during the reverse bias, the holes and electrons are pulled away from the junction, right? Not these ions. Electrons and holes are pulled away from the junction because they are free charge carriers. The width of the depletion region keeps on increasing. Whereas in the forward bias, you remember forward bias, it is like this. The width of the depletion region was decreasing. Width of the depletion region decreases. Actually, barrier potential also decreases during forward bias because electrons and holes are made to cross the junction. So width of the depletion region decreases, barrier potential decreases, and electrons and holes can move across the junction after a certain potential difference. But during reverse bias, the width of the depletion region starts increasing and there is a pressure on the depletion region and electrons and holes are pulled away from the junction instead of crossing the junction. They don't produce any current because they want to go here. These electrons want to go here. You can't produce a current by moving in the opposite direction like this. They have to move towards each other. So when the reverse bias potential is increased from 0 to certain value, you will find that the current in the diode is 0. Why? Because holes can't cross the junction. They have been pulled away to this side. Electrons can't cross the junction. They have been pulled away to this side. You see, this is positive. Positive of the battery attracts electrons. And the width of the depletion region goes on increasing. So there is a pressure on the junction. If you keep on increasing this, expecting that you will get current at certain stage, what happens is this diode junction breaks down. It breaks, simply it breaks, and diode is completely spoiled at that moment. So if the reverse bias is increased, suppose if you want me to draw the reverse bias graph, I will completely go to the third quadrant. You see, why third quadrant, sir? Current is reverse, voltage is reverse, biasing is reverse. We have connected P side to the negative. So reverse bias, voltage reverse, current reverse. You have minus minus on the third quadrant, right? Current is negative, voltage is also negative because it is in the reverse bias. But do we get any current? That is more important. So current here, voltage here. So I have to fix it here, right? In this quadrant. Voltage, current. That is what I am drawing here. Now actually, do we get any current? Yes. We get a very, very small amount of current during reverse bias. How come, sir? Reverse bias is avoiding the migration of electrons and holes, similar to the barrier potential. Because you see the polarity, they are very similar. But because when this barrier reverse bias voltage is too much, these electrons and holes which are minority carriers can move. What are minority carriers? Here, negative, minority carriers, minority carriers, minority carriers. See, they are having now a very good time because this positive may be attracted by this negative. This negative may be attracted by the positive. So majority carriers can't move. They can't move across the junction because this minus is attracting positive charges to this side, this positive is attracting them. So they are trying to move away. That doesn't produce current. But minority carriers can cross the junction. These negatives can move here, these holes can move here, but they are only minority. How much current they will produce? Very, very small amount of current, because you know the number of minority carriers are very, very less compared to the majority carriers. So if you are asked a simple question, a diode, does it conduct during forward bias? Yes, a diode conducts during forward bias. Which are the charge carriers responsible for the current during the forward bias? Majority carriers, because majority carriers can cross the junction because forward bias energizes them. It gives an extra energy to them. They can cross the barrier potential and they can conduct, right? If your student cannot cross the jump the compound, you can supply energy and you can make him to jump. Similarly, so here the forward bias can give it. What about reverse bias? No, it doesn't allow the charges to flow across. What charges? Majority carriers. But does it support the minority carriers? X. What is during reverse bias, current is mainly due to minority carriers, because for minority carriers it is forward bias. See, minus is connected to negative of the battery, plus is connected to positive of the battery. They conduct, but their current is very, very less because their numbers itself is very less. So during reverse bias, as you increase the voltage, you get a very, very small current, only this much amount of current, and this is the reverse bias current. And that current is very small, and it is only because of minority carriers. Okay, go on increasing the voltage, reverse voltage more and more. Remember, there is a pressure developed across the junction because it is the width of the depletion region keeps on increasing. Okay, at one moment what happens is junction breaks. Once the junction breaks, it is the actually breaking of many, many covalent bonds. You will get plenty of free electrons and holes, because when the atom breaks, there are many, many free electrons and holes created, and they cross the junction and they produce a very large current. So suddenly at high voltage you get a current, and this is called breakdown voltage. So what do you mean by breakdown voltage? Breaking means it is the damage to the atom. Remember, sir, once the breakdown voltage is reached, we are getting very good current, sir. But remember, diode junction is lost. This junction is lost, and it is not a reversible process. You can't get the diode once again back. It is lost, it is gone. So once you purchase a diode, you must be aware that its breakdown voltage shouldn't be crossed. So always when you purchase a diode, you will be given some catalog saying that this diode you pass only this much of maximum current to this diode, and the breakdown voltage of this diode is so much. What do you mean by that? You shouldn't go beyond the breakdown voltage. If you go beyond the breakdown voltage, there will be a breakdown and the junction breaks down and more amount of free charges will be created and it cannot be repaired. It is irreparable process. So once the breakdown is reached, high current flows. That is because of the breaking of the atoms or breaking of the molecules. So many electrons and holes will be created. So they cross the junction. So, but when you go to this area, so imagine that we are working with only this much. During reverse bias, that means when P region of the diode is connected to negative of the battery, N region is connected to the positive of the battery, you know that the diode doesn't conduct. Of course, there is a very small current. That's why I write here microamperes. This voltage is in volts. That is no problem. Within breakdown voltage, current is very, very small. That is because of minority carriers. So during reverse bias, diode does not conduct. Diode does not conduct during reverse bias, and its resistance is very high. It offers very high resistance. This is the speciality of the diode. Now suppose you have a wire connected to a battery, positive and negative. Current flows through the wire. Reverse the wire. Current flows through the wire. Wire has nothing property like that. If you connect the wire in the reverse way, no current flows, or like this. Suppose if you have a pipe, pass the water through the pipe like this, water flows. Pass the water in this direction, it flows. Wire conducts in any direction. What about diode? That is the speciality of the diode. Diode conducts in one direction, doesn't conduct in another direction. It is like a valve. Suppose you have a pipe, a very large diametrical pipe. If water is flowing through the pipe, and suppose there is a valve like this, there is a small groove and there is a movable window, say. When water flows in this direction, this window moves and gets stuck here. No water can flow now. But when the water flows from that side, this valve can open and water can flow. Understood? So as the water flows here, this valve is stuck. No water can flow. From the other side, if the water flows, this valve can open. So it can conduct in one direction, not in the other direction. We have such type of plants, right? They have a small bag-like arrangement and there is a wall at the above. When the insects come and sit on this wall, the valve opens and the insect falls inside. And the valve gets closed by automatically. And the insect can't come out because this valve doesn't open on the other side. Insects can go in but can't come out. So only entry ticket in one direction, not in the other direction. Insect is trapped inside. So many acids will be sprayed and insect will be killed and the plant eats it. So we have such type of. In biology you read all these things. Similarly, diode conducts during forward bias, allows the current to flow through during the forward bias, doesn't conduct during reverse bias. You have a block here, not like this, only like this. So there is a current like this. Still I have left with some points. I have to say that in the next class. I just remembered now. Just in the next class I have to remind and I have to do that. One is forbidden, not forbidden, that is donor level and acceptor level. That one I have to say. And another thing is here, what happens to the energy levels and so barrier potential in terms of energy levels. I have to say that. But still, major portion of the forward bias and reverse bias is over. We will meet in the next class with few more ideas of this and how that property of diode is used in different cases. Thanks for watching my class. We will meet in the next class with few more things, right, about diode. Thank you.